This is my solution for the problem that we did on Friday of week 7. And we started to talk about this idea of conservative interactions. And what that means is that mechanical energy is conserved. So how do we know if it's conserved? Well, it's conserved until it's not conserved. So it doesn't make a lot of sense, but basically the idea is that if there's an internal force that can convert mechanical energy into some other kind of energy, then mechanical energy is not conserved. But in the absence of those kinds of forces, then mechanical energy is conserved. Now this is different from momentum, because as long as the system is isolated, any of the forces exerting an impulse on objects within the system, if you sum their momentum, those are going to be conserved, the sum of the momentum. So the mechanical energy is conserved sometimes, but the momentum of the system is always conserved. And we did an example of two carts, and the forces between them were magnets. So you don't know that right off the bat, but I can tell you that the force that magnets exert are conservative forces, so the kinetic energy is conserved. And so we had the two things moving with equal speed, and we had a mass m and a mass 2m. And in all of these problems, we say that the sum of the momentum, we only have an x direction this time, is equal to the sum of the momentum in the y direction, in the x direction, and we calculate that before and after. And we say that the sum of the kinetic energy, no x or y direction at all, is the same before and after, because energy is just a scalar. So the question here was to find the motion of the carts after the collision. Okay, so let's do that. We'll set up this system of two equations. And so my two equations are that I have an mv and an mv for the two carts. Now momentum is a vector, so if I choose positive to the right, that means that the 2mv cart is going to the left, so that's a negative direction. And then I have a 1/2 mv squared plus a 1/2 2mv squared. And the momentum after, well, I don't really know what it is, so I'm just going to call it mv1 final and 2m v2 final. And I'm going to let them both be positive. You know, it might bounce back, but I guess we'll find that out. Okay, so 1/2 mv1f squared is the kinetic energy, and 1/2 2m v2f squared. So I can make these simpler by dividing through by the m's and dividing through by the 1/2. And I'll rewrite that equation now, or set of equations, as v minus 2v is v1f plus 2v2f, and v squared plus 2v squared is equal to v1f squared plus 2v2f squared. Okay, I'll simplify one more time, and the left side just becomes minus v1f plus 2v2f. And let's see, 3v squared is v1f squared plus 2v2f squared. Okay, now what do I do? Well, now what I have to do is I have to substitute, because I have two unknowns. So I have two equations and two unknowns. And so, and those unknowns are v1f and v2f. So I'm going to solve, I think I'm going to solve, let's see, I'll solve the top equation for V1f, and then I will plug that into the second equation. So I'm going to do that on the next page. So V1f is equal to 2V2f plus V, and then I'm going to substitute that into the bottom equation. So 3V squared is equal to V1f, so 2V2f plus V squared, plus 2V2f squared. Okay, so now I'm left with one equation. This is the one I'm going to solve. Of course, I can see it's going to be hairy because I'm going to end up with a quadratic, but that's okay. I'm going to plow forward here. So I'm going to get 3v squared, and I just do first outer inner last, so 4v2f squared plus 2 of them, so 4v2f v plus v squared plus 2v2f squared. Yep, now I'm going to group like terms, so I have a 4 here and a 2 here, and so I get 6v2f squared. I have my cross term here, so plus 4v2f v, and I have 2 of these constant terms, well, the constant in the sense that I was given them. So I'll subtract to the other side, and this is minus 2v squared. Now, I know it seems weird that you can solve something where some of the variables are actually variables and other of the letters are actually just numbers, but you can do that. So if you imagine just plugging in a number for v, then v2f would be your only variable. And but believe it or not, I think I can factor this one. So let's see. I need two numbers that multiply through to be 6, and I need two numbers that multiply through to be 2, and they have to have the opposite sign. So let's make this one, I think this, or 2v rather, I should say, and 1v. So let me try making this one negative and this one positive. So then for the first term, I would have, let's try a 6v2f and a 1v2f. So let's see, I'll just check my work here. So I would get this, the first term is 6v2f squared, and the last term is minus 2v squared. That part I know was going to be right. But now let's check to see if the inners and outers work out. So I've got a 6v2f and a minus 1v, and then I have a plus 2v and a 1v2f. So that's a minus 6, and a plus of 2 is minus 4. Oh, I almost had it. So this must be minus, this must be plus, so that I get the 6, this must be plus, and this must be minus, and so I get plus 4v2f v. Okay, so I got it actually. This is the answer right here. So all I have to do is solve for v2f. And you should notice that I actually have two solutions here. The first solution is that v2f could be equal to, well, let's see, if it was, if I solve that, I get 1/3 times v. So if you plug in a 1/3 times v, you'll find that you do get a solution. The other solution that I could get is that v2f is equal to minus v. But here's the thing. v2f equaling minus v, that means that the massive cart is going to the left. But that's actually the initial condition. So the math told us that that's actually if they didn't collide at all. So that's not really that interesting to us. It's this one that's far more interesting. So we get that v2f is equal to 1/3 v, and I can come way back from the top and solve for that V1F is 2 times my new thing plus V, which is equal to, let's see, 5/3 V. And I'm done.